Well, we have finished Maxwell's equations, and today we will see a couple of problems on how to apply Maxwell's equations. And if we have time, we will see several problems on application of boundary conditions, of time-dependent fields. Okay, these are the you already know these are the summary of Maxwell's equations from 1124 up to 1131. Okay, and here the summary of time-dependent potentials. Okay, and the summary of interface conditions for electric field and for magnetic fields, and also the summary of a phasor representation of any function, and also phasor representation of our fields, electric field and magnetic field. Okay, here are the time harmonic equations of or time harmonic representation of Maxwell's equations in the frequency domain. Okay, now let's start to solve a problem. The first problem: displacement current density JD. So let's read the problem. A magnetic flux density B, which is equal to y 0.1 cosine 100t and cosine multiplied by cosine 5z Tesla, exists in a linear isotropic homogeneous material characterized by epsilon and mu. Find displacement current density JD in the material if there are no source charges and current densities in material. So okay, well, how do we proceed in this problem? So we are given magnetic field with flux density B equal to y multiplied 0.1 multiplied by cosine 100t multiplied by cosine 5z. Okay, if we look to the magnetic flux density B, we can easily say that our magnetic flux density B has only one component, which is a component along y, and its magnitude is equal to this expression. Okay, 0.1 cosine 100t multiplied by cosine 5z. Now, okay, everyone is mute. And this magnetic field exists in a material with properties of electric permeability is epsilon, and magnetic permeability of material is mu. So we want to find displacement current density JD. How can we find JD? Okay, first of all, let's look to the mm, Maxwell's equations. Here are the Maxwell's equations, and from from the definitions we know that from the definition we know that the time derivative of electric flux density D is equal to the JD, or equal to equal to displacement current density JD. So, okay, we know that here JD equal to D over T, and okay, let me copy this and paste here just for okay, and we said JD is will be equal to, or is equal to, the electric flux density, derivative of electric flux density with respect to time. And by the okay, from the problem we can say that there are no source charges and current densities in material. It means that no source charge, the charge density, volumetric charge density is 0, and from here the no charge, and also no current densities. There is no current density. It means J is also 0 here. Okay, let me go to a new page. If I put the equation here, okay, from the problem this is equal to 0, and this is equal to JD. And now we know that JD, okay, we want to find the JD, displacement current density JD is equal to the rotor of H, or to the rotor of magnetic field intensity. What is H? H is 1 over mu multiplied by B, yes? And so let's compute H, or let's define H. H is equal to Y multiplied by 0.1 over mu multiplied by cosine 100 t multiplied by cosine 5z. This is our H. Now we want to compute the rotor of H. So okay, how do we compute the how do we compute the rotor of any generic vector field? In order to compute the rotor of any generic vector field, we use the matrix method, which is, I think, more convenient. So in the first row of our matrix is x, unit vectors x, y, and z. In the second row is the components of operator del, d dx, d dy, d dz, and in the third row the components of vector field. And if we apply this to our case, what we have the rotor of h will be equal to x, y, and z, d dx, d dy, d dz, component of h along x, component of h along y, component of h along z, and so first of all, let's look at our h. Our h has the same components as b, and we can say that h, or magnetic field intensity, has component only along y, and components along x and along z are 0. Component along x is 0, component along z is also 0. So we rewrite, okay, so now the rotor of h now will be equal to x, y, and z, d dx, d dy, d dz, and here hx is 0, we have component only along y, hy, and hz is also 0. So, and how do we compute the determinant of this matrix? First of all, we take the first row and first column. It is x multiplied. d dy multiplied by 0 is 0. d dz multiplied by hy. Now we have only minus d hy over dz. Okay. Now we take column and row which contains component y, d dx multiplied by 0, d dz multiplied by 0. Both are 0, so we don't care about this component, and we take the column and row which is containing z. What we have? d dx multiplied by hy, d dy multiplied by 0. So we have okay, plus z d hy, so d hy over dx equal. Okay, before computing these two derivatives, let's write one more time the component hy. Hy is equal. Now, when I write hy, I will write without unit vector y. Is equal to 0.1 over mu, 0.1 over mu multiplied by cosine 100t multiplied by cosine 5z. If we look to the component hy, we can easily see that hy is a function of z and t. Component hy is a function of z and t. Only the function of z and t. Now, and let's look to this term. Here we are taking the derivative of hy, derivative of this one, with respect to x. With derivative with respect to x. As we know that hy is the function of only z and t, it means hy is not the function of x. Hy is constant in terms of x. Okay, as hy is not the function of x, this term, this derivative, this term will be 0. And now let's look to this derivative. Here we are taking the derivative of hy with respect to z. We can see that, okay, hy is a function of z. It means that we can take the derivative with respect to z. Now let's take the derivative with respect to z, and what we will have. Okay, let me put it somewhere here, and this is something separate, and here it is equal. If we take the derivative of hy with respect to z, what we have? We have here minus. We have minus x unit vector. Unit vector x remains the same, remains unchanged, multiplied by 0.1 over mu is constant. 0.1 over mu is constant. Cosine 100t is also constant in terms of z. Okay, the term cosine 100t is also constant with respect to z. That's why this is also one of the coefficients, 100t multiplied. Now cosine 5z is not a constant, is function of z. Now if we take derivative of cosine 5z with respect to z is minus, okay, here 5 multiplied minus sine 5z. This minus and this minus gives us plus sine 5z. Okay, this is the rotor of H. Okay, let me check. Okay, and we said here that JD is equal to the rotor of H. JD is equal to X multiplied 5 multiplied by 0.1, 0.5 over mu multiplied by cosine 100t multiplied by sine 5z. Okay, we have found the displacement current density JD. Now, okay, now the problem finished. Okay, the next part of the problem. So we said that JD is equal to the derivative of displacement current electric flux density, sorry, the electric flux density by T. We defined that okay, JD as X multiplied 0.1 over mu X multiplied 0.5 over mu multiplied by cosine 100 t multiplied by cosine sorry, not cosine but sine 5z. Now if we want to find electric flux density D, can you find electric flux density D from this equation? It is very simple first order differential equation. Please try to calculate electric flux density D. Okay, now if we want to find the electric flux density D, we need just to take the integral of, so look, okay, I will write here in this page. Okay. One moment. Okay, look, we said the D over the T is equal to JD, yep, and the D is equal to will be equal to JD by the T, and the D itself, the electric flux density itself, will be equal to integral of JD by time, integral of JD by time. And simply, we have integral of x multiplied 0.5 over mu multiplied by cosine 100t multiplied by sine 5z dt by time. Okay, well, let me copy this to the new page because we cannot manage to fit here. So this integral equals to look, unit vector x in terms of time is constant. Sorry. Unit vector x in terms of time is constant. That's why it goes out of integral. 0.5 over mu is constant. 0.5 over mu is constant. Cosine 100t, okay, is not constant in terms of time. Sine 5z is constant. Sine 5z in terms of time is constant. Sine 5z goes out of integral, and in the integral we have cosine 100t dt. You just
ぼやまあまあ、コシンスカスタンタどうですか
sorry?
ぼやコシンスユスティンカスタンタどうです
Okay, look. Now we are dealing with t. Now the okay. Переменная. Yes, now we are dealing with in terms of t. In terms of t, cosine 100t is not constant. Sine 5z is constant in terms of t. Before we worked with z, that's why in terms of z, cosine 100t was constant. Okay, if we, now it's simple, we need to compute this integral is equal to simply sine 100t over 100 equals to x 0.5 over mu multiplied by sine 5z multiplied by we said sine 100t over 100 and plus some constant c1, or no, we need to write this constant. Or let me rewrite one more time. D, electric flux density D equals to this and equal to x okay, now 0.5 over 100 or 1 over 200. We may write, look, 0.5 over 100, we may write 1 over 200. We write 1 over 200 mu multiplied by sine 100t by sine 5Z. Electric flux density D is equal to this. Okay, is it clear now? Okay, let's move to a new problem. So let's continue. The next problem is 11.9. Okay, 11.9. So let's read the problem. What value of A and B are required if the two fields with electric field intensity E equal to Y 120p cosine blah blah blah, H is equal also Z AP cosine and 10 to the power 6 pt minus beta x. These two fields must satisfy Maxwell's equation. So if these two fields satisfy Maxwell's equation in a linear isotropic homogeneous medium with epsilon relative and mu relative equal to 4 and sigma which is equal to 0. So assume there are no current or charge densities in space. So J is 0, charge density rho is again 0. We need to find the values of A and beta. What are the values of A and beta so that the electric field intensity E and magnetic field intensity H satisfy Maxwell's equations. Okay, what are the values of A and beta?
Ustoz tenglamalar sistemasi qilib yechmaymizmi?
Yes.
Shu tenglama qo'shimcha ko'paytirib, ayirib qo'shib olsak chiqishi mumkin-da. Endi hali H bilan E ni berilganini yozib turib, ikkalasini juplab tenglamalar sistemasi qilsak,
bunday qilsak hozir P kosinuslar qisqarib ketadimi?
No.
yo hozir Bx bitta-ku ikkalasida ham bor Bx. Ko'ra turgan bo'lsangiz, o'sha Bx ni adini topib turib,
Okay.
shu Bx o'rniga qo'ysak,
so look, suggest your ideas. Let's discuss your ideas, and after, if you are right, we will continue, or if you are not, I will show the solution. Okay. Suggest your ideas. What should I write, or
Bilan plus qilish kerak shunda, to'g'rimi?
you are saying, okay, sorry, E plus H. No.
Yo'q, men Shahboz aytgan tushungan bo'lsam anaqa qilish kerak deb, to'g'ri o'zini anaqa funksiyaga o'xshatib
Okay, just tell me what to write. Shavos,
Oh,
where are you? Tell me what to write.
shu tinglamalar sistemasi edi, uni kosinus ichiga kirgizmaymiz-ku. Ustoz, bunday qilsa bo'ladimi? Y 120 pi kosinus 16 pt minus y ana kosinus ichiga ko'paytirib nima qilib yuborsak bo'ladimi?
120 pi cosine 10 to 6 pt and
Endi qo'shib yoping-da endi. Minus ana uni qilib olsa bo'ladimi, bo'lmaydimi demoqchi edim.
no.
Endi bx ga ko'paytirsak.
No.
Ko'z sochorsan.
No. Here, okay, look, pay attention. The argument of cosine is not just 10 to. The argument of cosine is not just this. The argument of cosine is the whole bracket. 10 to 6 pt minus beta x. This is the argument of cosine. Okay, you have a clue. Here it is saying what value of A and B are required if the two fields satisfy Maxwell's equations. Maxwell's equations. These two fields satisfy Maxwell's equations. You need to look to Maxwell's equations and find the right ones to use. Did you understand or not?
No. Hozir birinchi qiladigan ishimiz nimadan boshlaymiz, masalan, boshini?
First you need to read the problem carefully. I think no one understood the problem. We are given two fields. First is electric field, which with intensity is given, and the next is magnetic field, the intensity of which also given. And we have the constants A and beta in these two fields. We are interested in the values of A and beta so that these two fields satisfy Maxwell's equation. It means that these two equations must satisfy, or better, these two fields must satisfy Maxwell's equations. We go to Maxwell's equations and we see that Maxwell's equations containing electric field intensity and magnetic field intensity are these two, or these two. Doesn't matter. Doesn't matter which one do you want to use. I think this one is more convenient. Here, rotor of electric field intensity should be equal to the minus dB over dt, and the rotor of magnetic field intensity should be J plus the d over dt. Okay, let me copy these two equations and put here. And here we are given J is 0. We go back and say that J is 0. What about B? B is simply mu multiplied by H. What about D? Electric flux density is
Sigma ko'paytirilganmi?
epsilon multiplied by E. So,
Yeah.
okay, put, so we are given E here, yes? Sorry. Here we are given E, electric field intensity. What about H? H is also given. So what about B? B we can find. What about D? D we can find, yes? Now try to write a system of equations here. Try to write a system of equations, and after that we will see also. Can you do this by yourself?
Buni hozir endi 4 ga ko'paytirib chiqamizmi?
Not exactly. Okay, let me show you.
Men tushunmadim. Ani men mu cos J 0 ga teng deb turib.
Here J. Okay, it is given in our problem. Assume that there are no current and charge densities in space. No current density and charge density means that current density, if there is no current density will be equal to 0, yes? If there is no anything, the measure of that thing will be 0. No charge density. Charge density is defined by rho. No charge density means that rho is also equal to 0. That's why here, here J is going to be 0, B is not 0, D is not 0. B is by definition is equal to mu multiplied by H, and D by definition is epsilon multiplied by electric field intensity. And where the mu is equal to mu R multiplied mu 0, and epsilon is also given epsilon R multiplied by epsilon 0. These are the basic things. Okay, let me write the system of equations. Rotor of electric field intensity is equal to minus the B over the better, let me write instead of B mu H. Okay. So minus mu dH over the T. Rotor of magnetic field intensity H is equal to the D over, so epsilon the electric field over the T. So we have a system equation with two equations. Now, first of all, we need to compute the rotor of electric field equals to what? Rotor of magnetic field equals to what? And from the other side, minus mu dH over the T equals to what? And also epsilon the E over the T equals to what? So can you compute these values? Can you try to compute these values?
Yeah.
Okay, you have 10 minutes. Try to compute these values, these 4 values. After that, we will continue our lesson.
Yeah.